Next, we discuss about the limitations of Ohm's law. First one. Non-ohmic materials. Ohm's law only applies to ohmic conductors, example metals, where resistance remains constant. It means, Ohm's law, stating V equals to IR where resistance R is constant, only applies to ohmic conductors like metals. It doesn't apply to nonlinear devices like diodes, transistors, or thermistors, where current and voltage do not have a linear relationship. It means, non-ohmic conductors, also known as nonlinear resistors, have resistance that changes with voltage or current, making them nonlinear. Examples of non-ohmic devices include diodes, transistors, thermistors, and light bulb filaments. Ohmic conductors means, these materials exhibit a linear relationship between voltage and current, meaning their resistance remains constant regardless of the applied voltage. Non-ohmic conductors means, these materials do not follow Ohm's law. Their resistance changes depending on the applied voltage or current, leading to a nonlinear relationship between voltage and current. Examples of non-ohmic devices are diodes, transistors, thermistors, light bulb filaments. Diodes means allow current to flow in only one direction, and their behavior is nonlinear. Transistors means used to amplify or switch electronic signals, and their behavior is also nonlinear. Thermistors means devices whose resistance changes with temperature, exhibiting a nonlinear relationship. Light bulb filaments means their resistance increases significantly as the temperature increases, making them non-ohmic. Second one, temperature dependence. Resistance is assumed constant, but in reality, resistance changes with temperature. It means, while resistance is often assumed constant in calculations, it's a simplified view. In reality, resistance changes with temperature, particularly in materials like metals and semiconductors. This change is due to how temperature affects the movement and collisions of electrons within the material. Ohm's law may not hold if the temperature significantly affects the materials. Resistance, example in filaments or semiconductors. It means, Ohm's law, which states that voltage and current are directly proportional at a constant temperature, can fail when temperature significantly affects material resistance. This is particularly true for materials like filaments in light bulbs and semiconductors, where temperature changes drastically impact their resistance. However, many materials, especially those used in filaments and semiconductors, have resistance that varies significantly with temperature. Third one, high-frequency circuits. In AC circuits with high frequencies, inductive and capacitive reactance come into play. In AC circuits, at higher frequencies, both inductive and capacitive reactance become significant, impacting the flow of current. Inductive reactance increases with frequency, while capacitive reactance decreases with frequency. Inductive reactance is the opposition to the flow of current in an AC circuit caused by inductors. Capacitive reactance is the opposition to the flow of current in an AC circuit by capacitors. Ohm's law does not account for phase differences and impedance in such cases. In simple terms, Ohm's law, which states V equals to IR, voltage equals current times resistance, primarily applies to simple DC circuits with purely resistive elements. In AC circuits or circuits containing reactive elements like capacitors and inductors, where impedance and phase differences exist, Ohm's law needs modification or extended to account for these factors. The standard Ohm's law formula is not sufficient for AC circuits because it doesn't consider the phase difference between voltage and current. In AC circuits, reactive elements like capacitors and inductors introduce reactive impedance, which opposes the flow of AC current. Fourth one, superconductors. In superconducting materials, at very low temperatures, resistance drops to 0. Ohm's law becomes undefined as R equals to 0. It means Ohm's law, V equals to IR, generally states that the current through a conductor is directly proportional to the voltage across it, with resistance as the constant of proportionality. However, this law has limitations, and it doesn't apply to superconductors. Superconductors have zero electrical resistance at very low temperatures, meaning current can flow without any voltage applied, violating Ohm's law. Fifth one, vacuum tubes and gas discharge lamps. These devices exhibit nonlinear IV characteristics and do not follow Ohm's law. It means Ohm's law, which states V equals to IR, voltage equals current times resistance, doesn't accurately describe the relationship between voltage and current in vacuum tubes and gas discharge lamps. These devices are non-ohmic, meaning their resistance changes with voltage and current, making a linear relationship impossible. Sixth one, non-uniform materials. In materials where the structure or composition changes throughout, Ohm's law may not apply uniformly. In materials where the structure or composition changes significantly throughout, Ohm's law may not apply uniformly or at all. Ohm's law, which states that current is directly proportional to voltage, V equals to IR, is a simplification that works well for many conductive materials under relatively constant conditions. However, it doesn't hold true for materials that exhibit nonlinear behavior, where resistance changes with voltage or current. Next we discuss about the Ohm's law applications. Ohm's law, which states that the current in a circuit is directly proportional to the voltage and inversely proportional to the resistance V is equals to IR, has numerous applications in electrical engineering and beyond. It's used for designing circuits, calculating power, and troubleshooting electrical problems. Ohm's law also helps in understanding how different electrical devices, like resistors and ammeters, work. First one. Designing electrical circuits. Used to calculate the correct resistor values to control current flow. Ohm's law, R is equals to V divided by I, is used to calculate resistor values for controlling current flow in circuits. It establishes the relationship between voltage, V, current, I, and resistance, R. By rearranging the equation, you can determine the resistance needed to limit current to a desired level. How Ohm's law is used. We know R equals to V divided by I. This formula calculates resistance when voltage and current are known. V equals to IR. This version calculates voltage when current and resistance are known. I equals to V divided by R. This version calculates current when voltage and resistance are known. Ensures components receive appropriate voltage and current levels. It means Ohm's law is crucial for ensuring components receive appropriate voltage and current levels. It defines the relationship between voltage, current, and resistance in a circuit, allowing for accurate design and analysis to prevent damage or malfunction. By understanding this relationship, engineers and designers can select components and design circuits that operate within safe and effective parameters. Second one, determining unknown values. Helps in finding an unknown voltage V, current I, or resistance R when the other two are known. In simple terms, Ohm's law relates voltage V, current I, and resistance R in a circuit. The fundamental equation is V equals to IR, where V represents voltage, I represents current, and R represents resistance. You can use this equation to find any of these values if you know the other two. To finding voltage V. If you know the current I and resistance R, you can calculate the voltage using V equals to IR. Finding current I. If you know the voltage V and resistance R, you can calculate the current using I equals V divided by R. Finding resistance R. If you know the voltage V and current I, you can calculate the resistance using R equals to V divided by I. Third one, power calculations. Ohm's law can be used to calculate power in an electrical circuit. Power P in watts can be determined using the following formulas. First one, P equals to VI. Second one, P equals to I square R. Third one, P equals to V square divided by R, where I is current amperes, V is voltage volts, and R is resistance ohms. Power equals voltage into current. The most basic relationship is power P equals voltage V multiplied by current I. This is often written as P equals to IV. Power equals to current squared into resistance. By substituting V equals to IR from Ohm's law into the power equation P equals to IV, you get P equals to I square R. Power equals to voltage squared divided by resistance. Similarly, by substituting I equals to V divided by R from Ohm's law into the power equation P equals to IV, you get P equals to V squared divided by R. The power in an electrical circuit can be calculated using any of these formulas, depending on which variables, voltage, current, or resistance are known. Fourth one, short circuit analysis. Helps identify excessive current that could damage components. It means Ohm's law V equals to IR can be applied to short circuit analysis, even though the resistance in a short circuit is very low. A short circuit is essentially a path of very low resistance, often considered close to zero, and Ohm's law can be used to analyze the current and voltage in such situations. Fifth one, troubleshooting electrical equipment. Technicians use Ohm's law to detect faults in circuits by measuring voltage and current. It means Ohm's law V equals to IR is a fundamental tool for troubleshooting electrical equipment. It helps engineers and technicians identify issues like short circuits, component failures, and voltage drops by analyzing the relationship between voltage, current, and resistance. By measuring these values, they can pinpoint the source of the problem and determine the appropriate repair or replacement needed. Sixth one. Battery and power supply sizing. Ensures correct voltage and current are delivered to devices. Ohm's law, V equals to IR, is crucial for battery and power supply sizing because it helps determine the required voltage, current, and resistance in a circuit. By understanding the relationship between these parameters, engineers can design power supplies that efficiently deliver the necessary voltage and current to a load, ensuring proper battery operation and circuit functionality. Seventh one. LED and transistor circuits. Used to choose proper resistors to limit current through LEDs or set biasing in transistor circuits. It means Ohm's law, V equals to IR, doesn't directly apply to LEDs and transistors in the same way it applies to resistors. While Ohm's law can help calculate the resistance needed to limit current in an LED circuit, LEDs are not ohmic components, meaning the relationship between voltage and current is not linear. Transistors also have nonlinear current voltage characteristics. Eighth one. Household wiring. Assists electricians in selecting wire gauges and fuse ratings. It means Ohm's law, which states V equals to IR, voltage equals to current into resistance, plays a crucial role in helping electricians select appropriate wire gauges and fuse ratings. By understanding Ohm's law, electricians can calculate current flow and voltage drop, ensuring safe and reliable electrical systems. Ninth one. Load balancing. Ensures that the current is evenly distributed in multi-load circuits. It means, in large-scale power systems, Ohm's law is used to calculate current distribution in parallel circuits, ensuring that loads are evenly distributed across multiple components and preventing overloads. Padmam Hemam. Thank you.